So hello friends, welcome to another video. So in this video we are going to talk about the basic fundamental principle of electric circuit analysis. Previously we have seen in our many videos. So we worked on first of all source transformation, and then its problem solving. Then 3 we have went to nodal analysis, and then its problem solving. And then on the fifth one, which was mesh and analysis. And then at the sixth we have problems. Now these all are somewhere we have used the fundamental law in circuit theory, which is KVL or Kirchhoff's voltage law. So this is very fundamental law as like Newton's law in our classical mechanics. So this law we have already used, but we don't know that what are the implications and how it comes into effect and what is its significance. So hi, this is Sujay Shah, Associate Professor on Department of Basic Science of SR University. We are going to discuss about the Kirchhoff's voltage law, the basic and very fundamental law in electric circuit theory, and with that we will have some kind of concept of this law and its applications. Okay, so let's start. So as the name suggests that this was discovered by Gustav Robert Kirchhoff, you don't really have to remember the full name of the person depicted here, but we have to remember the pronunciation of this law, which is Kirchhoff's. Somebody also pronounces Kirchhoff's law or Kirchhoff's law or Kirchhoff's law, but I will be sticking to Kirchhoff's law. Okay, that's a German word, and time to time it varies a lot, so different people pronounce it differently. Anyways, name does not matter, but the matter is what matters most, the applications of this law. Okay, so Kirchhoff was a German physicist and he was working on different circuits, and he saw that while analyzing different circuits, he saw that he discovered actually two laws. One is Kirchhoff's voltage law, or in short KVL, Kirchhoff's voltage law, based on the law of conservation of energy, and the other one is the Kirchhoff's current law, or KCL, based on the law of conservation. So in this video we are going to talk about Kirchhoff's voltage law, and in the next lecture or in the next video we are going to learn about Kirchhoff's current law. Now Kirchhoff's voltage law is no new thing. It is basically the manifestation of law of conservation of energy in electrical circuit. Like electrical circuit also runs on electrical energy, which is a form of energy. So as we know, the conservation of energy states that energy cannot be created nor destroyed, which can be taken to electrical energies also, that electrical energy cannot be created nor neither destroyed, and that is actually tells you about the Kirchhoff's voltage law. So this is something which is pretty new. Looks like pretty new in electrical circuitry, but it was already there. Like before Kirchhoff's, people were aware of the law of conservation of energy. Till now, the law of conservation of energy is valid. So of course there are exceptions. If you are interested in, we can also talk about those parts. But for today, let us consider that energy cannot be created nor destroyed. Especially electrical energy cannot be created or destroyed, and for virtue of it we get Kirchhoff's voltage. Okay. Now what Kirchhoff actually did was, the first of all we need to know the basic idea or the basic statement of Kirchhoff's law. What Kirchhoff see? See, laws cannot be proven. We cannot prove law. Theorems can be proven. So let's say, so I can write it down. Laws can't be proven. It is impossible to prove a law because law is something how nature works, and we can only have a statement of it, a one mathematical or some statement we can have. So it is basically like a it's like a statement. Okay. Now what Kirchhoff actually told to us, he told that the algebraic sum, remember that whatever it is, there are terms which is important. The algebraic sum of voltages around a closed loop at any instant is equal to 0. So there are 1, 2, 3, 4, 5 uh, phrases are there. So algebraic sum. Algebraic sum means it's basically the addition of voltages. Addition of voltages around a closed loop. So in a circuit, if you find any closed loop, then you add the voltage one by one. Closed loop means the loop does not have any kind of open hand or open or dangling bond or something. It does not, it's a closed loop at any instant of time. At any instant of time means that it does not depend upon when you started your clock, is equal to 0. So the algebraic sum of the voltages across a closed loop is equal to 0 at any instant. Okay, so a loop, now what is a loop? A loop is a path that terminates at the same node where it started. So now we came to know a new term called node, and which is already we have known from our nodal analysis that node is a point where two or more circuit element meets. Okay, now this loop is a, so we have already seen that it terminates at the same node where it started from. So that is a one particular, so a loop can be like, for example, let's say I have this kind of circuit. So this kind of circuit, so this is one loop, so this is one loop, this one is one loop. It originates here and it ends here, and this one is also a loop where it originates here and also it comes at this point. So in this circuit there are two loops present in this circuit, and if you can calculate the voltage drop across this element and this element, it will be algebraically it will be equal to 0. Similarly, if we consider this loop, the second loop on the right hand side, the voltage drop across this and this will be equal to 0. Okay, so this is something we have to, first we have to accept that this is the law, and we will see that if this law is valid, then many things become simpler. This was the observation by Kirchhoff, and he presented in a mathematical way. So mathematically, the voltage drop across any closed loop, is given by the mathematical, it is the voltage drop across the loop is given by 0. Okay, now Vn is the nth voltage drop, nth element's voltage drop. So this is element number 1, this is 2, this is 3, and so on so forth. Okay, so as I told, Vn is the nth element's voltage in the loop. Okay, and n is the number of elements in the loop. There might be like n is any natural number, so n can be any number. Okay, now the statement of algebraic sum of the voltage around a closed loop you might find is difficult to understand. Okay, there is a voltage source which can be positive polarity or negative polarity and blah blah blah. So that is something you may be having a hard time to understand. But what I can do, I can tell you that there is another alternative statement of KVL is available, which states that the algebraic sum of the voltage sources is equal to the algebraic sum of the voltage drop that are present in the loop. So which is rather make more sense than the previous statement. What is tells that in a loop there might be elements which are not sources. Like here it is a resistance and this is a voltage source. Now the Kirchhoff's law tells you that the drop across this voltage source, the drop across this voltage source will be equal to the drops across these elements. So it states that the voltage drop across this loop, the sum of the voltages of the sources, which is only one loop, one voltage source on the left hand side loop, will be equal to the voltage drop across these resistances. Similarly, on the right hand side, there are two voltage sources. So sum of these voltage sources, sum of the algebraic sum of the voltage sources here will be equal to drop across these two resistors. Right? So this is something, the alternate voltage, and this one I have used many times in your problem solving by nodal or mesh analysis or source transformation. We have seen it many times. So this is something we have to assume or understand. Now this is the algebraic sum of the voltage of the source. Of course, it means that it has to have kind of magnitude and direction. So it is not like a simple algebraic sum. So as the voltage can be positive or negative with respect to some point, so of course the sum of the voltages has to have some kind of direction, right? So how to do that? Now let us say a particular element has terminals which is positive and negative. Now you are counting the voltage or calculating or taking the voltages in the same direction from positive to negative. Then we will say that that voltage is negative. So this is the convention actually. So if you are taking the voltage of a particular element which has positive and negative terminal from left to right, and you are taking in the same left to right direction, then of course it will be negative. Now left to right, up to down, this depends upon where you are taking. So let's say here, if you say, so if you take the direction of the current on the clockwise direction, so we can say that the direction, so the drop across this will be, it is so we can say that, so this is positive, this is negative. So of course this terminal, this point should be positive and then negative. Then also here it will be negative and positive, right? So positive, negative, and alternately it will have. Now you are taking on clockwise direction, so it will come from negative to positive. So if you take from negative to positive, it's a positive voltage. If you go through positive to negative, it's a negative voltage. So accordingly you have to choose. Okay, same thing. So if you have any element, let's say in this loop, so this is positive, this is negative. So of course this will be positive, this will be negative. So then this will be positive, this will be negative. Same positive and negative. Now you are taking loop in this direction. So of course it is going from negative to positive. So if it is going from negative to positive, this will be positive voltage. This will be positive voltage. Now this is going from positive to negative, then it will be negative contribution, then it will be negative to positive, it will be positive contribution, and it is also negative to positive, it will be positive contribution. Now you add up and it will go to 0. And that's the basic convention. Now if you are still unable to digest, we will get one example where you can actually feel that why we are taking in this way, okay, or more rigorous, and that convention I have used and I am going to use in our subsequent talks. Okay. Now already we have discussed about that there is serves as a fundamental principle of mesh analysis, like Newton's law in classical mechanics. Also, engineers can effectively predict that, manage voltage fluctuation, ensure system stability, and so on and so forth. And KVL is employed in lighting design, analyze the optimization of the energy, lamps, bulbs, electronics device, and so on. So if you have kind of mathematical like know-how of how much amount of energy needed, what is the optimization problem, that we can actually capture or actually see from the Kirchhoff's voltage. It can be done actually, but that is no depth. We can add in our subsequent lectures if you wish to. So like tell me in the comment box, right? Now this is actually we actually deduce it from our like we take an example. So here Vs is a voltage source and Z1, Z2, Z3 are the resistances. And now these are the polarity of positive and negative. So what I was telling you that this is positive and this is negative. So that means this will be positive, this will be negative, this will be positive, negative, positive, and negative. Now you count clockwise direction. So if you count for clockwise direction, so we are going from negative to positive, so it is positive contribution. Now you are going from positive to negative, then negative contribution, and so on. So you have 3 negative contribution and 1 positive contribution gives rise to the 0, that is which is the Kirchhoff's voltage law, and which is given by Vs equal to the source of the voltages is equal to the sum of the voltage drop across the loop. Now this was the statement of the first statement of the Kirchhoff's law, and this is the second statement of the Kirchhoff's law. So second statement comes through the first statement, so which is obviously kind of obvious that okay, from one statement the other, this is nothing new, so that is we can have. Now KVL is a law of conservation of energy. Why? That if any charge originates from this voltage source, it can go and it can come back, so the total work done by the charge will be 0 because the displacement is 0, and hence there is no loss of energy. So basically it's so whatever energy is utilized, that has been dissipated and that has been consumed, so ultimately the work done by the particular charge will be 0, and that tells you about the conservation of energy. We have already seen our mesh analysis problem, the power supply and the power dissipated, they are actually the same. Okay, now let us take a formal example of this particular problem. So here we see that find I current and the voltage drop across the 15 ohm resistance. So how to do that? So we have a circuit, a plain circuit having two voltage sources of 5 volts and 2 volts, and there is there is 3 resistances, 5, 10 and 15. Now let us take this to be as our first battery. So even if there are 2 battery or 2 voltage source, you can choose any of to start with. So here we can designate this as positive, this as negative, so it become positive and negative. This become positive and negative. This also become, like, we cannot say here what is happening, and this also positive, negative, then we cannot say, then it will be positive and negative. So then it will be done actually. So what we can do, we can still say positive, negative, then we can say as positive and negative, then positive and negative, then we are done with, like positive, negative, then we can still say it's positive and negative, and then positive, negative, correct? Yes, so we'll keep in that sense. Okay, now so we are going to calculate, we are going to say that the current is flowing on the clockwise direction, or we are going to take the count as clockwise direction. Okay, we will count here. So now here the current, we are going from negative to positive direction, so it will be positive 5 volt, then we add, it's a sum, right? So it's a sum. So now we are going from positive to negative. So now if you go from positive to negative, then obviously the voltage drop across the voltage drop across the 5 ohm resistance must be negative, plus, again we are going from positive to negative, so then it will be negative V10 ohm. Then we are going from positive to negative of this voltage source, so it will be negative 2 volt, plus, so we are again going from positive to negative of this 15 ohm resistance, so it will be 15, sorry, so it will be like V 15 ohm, and that must be equal to 0. Okay, now we can say that, let us say the current flowing through this circuit is I, because there is no other loop available. So we can say that 5 plus. So the voltage drop across the 5 ohm resistance will be V equal to IR, and which is nothing but, so this negative plus positive become negative, so V equal to IR. Let us consider the current is I, and the resistance is 5, so it is 5I. Then we can say that this is 10I minus 2 plus, sorry, there has to be one negative sign here because that also negative, so this is minus 15I equal to 0. Now we can say that, so what is available here, so this is 5, 10 and 15, so this is 15 plus 15, 30, so 30I equal to 3, just simplification, and then I equal to 3 over 30 equal to 0.1 ampere. So this is pretty straightforward. It is pretty straightforward that we have calculated the current through a circuit where multiple number of resistances and multiple number of sources, voltage sources are present. Okay, so in the next page we actually have calculated this, and the second part of the problem was the voltage across the 15 ohm resistor. So voltage across the 15 ohm resistance was 15 ohm, V15 ohm equal to that current I times R. So current was calculated to be 0.1, multiplied R was 15, and then it is 1.54. Remember that we have chosen, or the current, actually the sequence of the voltage sources we have taken is basically chosen as a clockwise direction, and that's why this was our starting point, positive and negative, and then we have done in this way, like this way. So this is something you can find it as a weird thing, but let us say take my convention, and that will be more easier. So be careful here, be more attentive here, so we'll do in a different manner. So what we have done, so what we can do here, we can do in a different way. So before even you do the calculation for any mesh analysis or KVL, so any KVL you can start with the problem of taking the loop current as clockwise direction and say this is I. Okay. Now the second statement, if you remember correctly, the second statement of the KVL was the sum of voltages of the sources is equal to the sum of the drops, and which is make more sense. Now you have taken the current in the clockwise direction. Now let us see. Now this current is originated like this, and it is moving like this way, right? If you take this like that way, this current in this clockwise direction, then the current originates from this positive terminal of the 5 volt source, and it originates from the negative terminal of the 2 volt source. Now if any current is coming out of the positive terminal of any voltage source, then the voltage of the source must be positive. Okay, and if current originates from the negative terminal of any voltage source, that source voltage must be negative. And these two these two has to be added as the sum of the source voltages, and that should be on the left hand side. Okay, so coming again, that we take loop current to be clockwise direction. Now due to virtue of this loop current originates from the positive terminal of 5 volt, and current also originates from the negative terminal of this 2 volt. So for 5 volt it must be positive because it originates from its positive terminal. For 2 volt it is negative because it is originates from its negative terminal, and they will be added. And now the voltage drop is simple, the algebraic sum. Is the algebraic sum, and which we can directly say I equal to 3 over 30 equal to 0.1. So it is straightforward. It is much more easier and convenient way to calculate the current of any loop, and then we can say that this 15 ohm, the voltage drop across the 15 ohm resistance is 0.1 times 15 equal to 1.5 volts. So this is pretty straightforward, and this statement I like actually, and you can also follow any of the convention, but I choose the second convention because it is more convenient to me. Okay. Now let us consider another particular example where we actually calculate the voltage drop between two terminals of like two like circuit. So this is another circuit. You can see that it looks like a more complex kind of circuit, but we can solve it. So this one is, we can flip this circuit to 180 degree, and what we can live with, what we can live actually, if you flip this, if you can flip this circuit into this, you can say that this AB arm comes to here, AB arm, and then it becomes more simpler. Correct. Instead of having a different kind of thing, it's become more simpler. Now same thing, if we want to calculate the voltage difference between C and E, which is VCE, we need to calculate the VCE. So how to do that? Now first of all, we have to calculate the current flowing through these loops, and then we assume that what are the loop currents. So let us consider on the left hand side the loop A, B, C, D having I1 current, and on the right hand side the loop E, F, G, H having current I2. Now I1 current, if it is flowing through the left hand side one, so then you can say that this is positive, this is negative, then this is also positive, negative, positive, negative, positive, and negative. Now the current is originating, current is actually going from positive terminal. So then we can have, and here the current is going from positive terminal to the negative terminal. So then it contributes to, this should be 1, typo. So this is 9I1, negative 9I1, because it is coming from negative to positive. Then positive 20, this is 20 volts, and this is 40 volts. Then minus 6I1, because this is positive to negative, the current is moving from positive negative terminal of this AB hand, and this minus 5I1. So you can calculate and simplify and get I1 equal to 1 ampere. Similarly, from the right hand loop, the current on the, we can say this is positive negative, then it is positive negative, and so on. So now you can see that if we take the current as this, so it is current originating from, it is going from G to F, it is counterclockwise. Then so it is minus 8I2 for the same reason, then minus 5I2 plus 40 equal to 0. Then you simplify and get 3.07 ampere as the I2 current. Now the crucial part. Now we need to calculate the voltage drop across these two terminals. Okay, so it is very obvious that some current, so which one is higher, which terminal has higher potential, that we don't know. But what we know, that this, in this loop, if we just imagine that okay, there is some kind of some resistance was there. If there is no resistance, means the drop across it will be zero, because there will be no current passing through, because the drop is actually zero. So there is no, because here you have nothing. So resistance in one sense it is infinite, but the current is actually zero. But we can still have the potential difference between these two points. Okay, so what we can do, we can get that. So the current is the drop across. So there are three in this E, H, B, C hand. There are actually three sources are there. One is, so the drop across this 5 ohm resistance is minus 5I2, as it is connected, as the I2 current is going its positive terminal to negative terminal. Now this HI, this is also originating. If you can think that, okay, the current is actually flowing from E to C. If you think that in that way, or it is the, so C, maybe you can think that C is at higher voltage or something. Then it is going from the H to B. It's pretty hard to digest, and then the current is going from B to C, and it is also negative, because we are going from the positive terminal, negative terminal of this ohm, of this resistance, and then we add VCE, because that's the potential here, and they must be equal to 0. They must be equal to 0, because the total voltage drop must be equal to 0, because there is no other things available here. Okay, now it is hard to digest, but maybe you can write down in the comment that what is going on here, what's wrong actually, and this gives you VC equal to 10.35 volts. So that is one particular Kirchhoff's laws application, and hopefully you have understood most of the lecture. If not, then tell me in the comment box. We will still clarify, and hopefully we'll meet in our next session of Kirchhoff's current law. So up to then, have a very good day, and hopefully we'll meet again, and keep smiling. Have a good day. Bye bye.